So I was hoping when I sent the email out that you spoke Liber fluently. When I said you should do the synthesis problem set, which is problems 40 and 50, what I was really saying is one of those problems is going to appear on the quiz. Hopefully you understood that. So the first quiz question was, in fact, chapter 17, number 50, part A. Just to take this aldehyde, and add an alpha group in the places where that hydrogen was. So we're forming a new CC bond. And because that new CC bond is not in the position alpha to the carbonyl group, right? It's not on this carbon. That means that that is going to be formed with a Grignard reagent, or an organic metallic. So either alpha magnesium bromide or an alpha lithium is going to form that new CC bond. So if we're working backwards, in order to form that new CC bond, then we're going to need that oxygen to be a carbonyl group. And then we add a Grignard reagent to a ketone to make the tertiary alcohol. But the problem is that group is also a carbonyl group. So in order to make a new CC bond here, but not make a new CC bond there, we have to protect this. So we're going to make an acetal out of this before we do anything else in the mechanism. So step one will be to do the same thing that we did on the previous quiz, quiz 2, which is to convert this carbonyl group to an acetal using ethylene glycol. Now we can oxidize that alcohol, but we have to be very careful how we oxidize that alcohol, because this is acid sensitive. Even though that's a secondary alcohol, and you could ordinarily use potassium dichromate in sulfuric acid and water, if you do that in this case, you're going to take that protecting group off. So it's important to use a neutral oxidizing agent like PCC or PDC to avoid the acid, so you don't take that protecting group off prematurely. That generates the carbonyl group that we need, and we can now either add methyl lithium or methyl magnesium bromide in ether. That's going to make that new CC bond. And then when we do the aqueous acid workup, in addition to protonating this oxygen, it's also going to remove that protecting group, and that will generate a final product. So it's actually several steps. Step one, protect. Step two, oxidize. Step three, organometallic. The new CC bond. And then step four, deprotect. One of the problems with using protecting group chemistry like this is you have two steps in there, one to put the protecting group on and one to take the protecting group off. So you've increased the number of steps, and if your yields are not very good, the more protection and deprotection steps you have, the less compound you end up getting. So there's a lot of emphasis now in modern organic chemistry to try to figure out how to do reactions that don't require protecting groups. But unfortunately, the organometallic reactions with lithiums and magnesium almost always require protecting groups because they're so basic. So you'll notice if you continue in organic chemistry that there's a lot more emphasis on using transition metals and catalytic processes in organometallics that are not so strong to base. Anyway, so that one was 1750A. While we're here on chapter 17, problem 50, I want to take a look at problem C. Are there any questions on A before I move on? Nobody's typing, so I'll take that as a no. So I want to take a look at problem 1750C, because that's a problem I think you'll have great difficulty with, because it requires a reaction from last semester that I know I didn't emphasize, and I suspect Dr. Pissner may not have emphasized either. So we're making this hemiacetal, and we're making for this linear, this would be 3-chloro, 1-propanol. And I mentioned when we were talking about acetal protecting groups that alcohol protecting groups were probably covered last semester, and Dr. Pissner may have covered it more than I did, but he may not either. The first thing with this is to recognize which atom is which. So this oxygen is this one, which means that this CH2 is here. So if we number our atoms, the 3 carbons from our starting material are here. Is that the right product? Now there's a CH3 here as well. So that means that this is the new CC bond. And identifying which is the right the new CC bond is the first step to solving the problem. So we're going to be adding this piece. Working backwards, that hemiacetal came from the cyclization of the alcohol. So there's our new CC bond. And this hemiacetal would form spontaneously from this carbonyl compound because the alcohol is so close to the carbonyl that it can collide with it readily. So just like in sugar chemistry, the compound is going to exist in aqueous solution mostly as a hemiacetal form. So the problem is how to make this new CC bond in the presence of the alcohol, because this is case sensitive. Which means that we need to protect the alcohol before we can convert this to an organometallic and add it to acetaldehyde. That's how we're going to get those 2 new carbons in there. So there are a couple of different ways of protecting the alcohol group. One of which is covered in chapter 9 of our textbook, and it's probably covered in Klein as well, and that's to use a T-butyl ether. So if I take this alcohol and I treat it with isobutene, and usually HF, because fluoride is not a great nucleophile, which means that when I protonate this, the fluoride isn't going to compete. The alcohol is actually going to be the better nucleophile, and you will end up forming kebutyl ether like that. The ethers are base stable. This would be acid sensitive. So as long as we avoid acid and do basic reactions, we can avoid messing with that piece. So now we're going to insert magnesium in there. All right, adding magnesium and ether. I'm just going to abbreviate that with a little cross. And we can add the acetaldehyde. Also in ether. So then we have, I'm just going to bring that molecule over here and redraw it. So we've now got our 5 carbons. We need to take this and oxidize it back up. And in this case, if we treat this with aqueous acid, in the presence of A2Cr2O7, that will take that protecting group off as well. And then in the presence of aqueous acid, you'll protonate this oxygen, and you can roll around and form the hemiacetal as well. But the key is the protection of the alcohol functional group as that tert-butyl ether. That's the reaction that's covered in our book. I know I didn't emphasize it. I'm not sure if Dr. Pfister talked about that one. But I suspect if Dr. Pfister did emphasize protection of an alcohol, since he often uses the same notes that Dr. Thomas works from, he probably protected that alcohol differently. The other common protecting group for an alcohol is as a trimethyl silyl group. So he probably treated it with this. This is TMS, trimethyl silyl. And the trimethyl silyl functional group reacts by an SN2 pathway. Because silicon is significantly bigger than carbon, even though this is kind of a tertiary position, there's much less steric hindrance, you can still do the SN2 pathway at silicon. And this is another acid labile, but base stable functional group. Does that seem familiar to the two of you that were in Dr. Pfister's class? Did he talk about the trimethyl silyl protecting group for alcohols?
If he did, I don't remember.
Okay.
It doesn't really look familiar.
I know Dr. Thomas does when she's in the alcohol chapter, and since Pfister often uses her notes, I figured he might have as well. Do you remember seeing the isobutyl group, or that tertiary butyl from isobutene, or did he not cover that one either?
Say that again, it
Did-
cut out a little bit.
Did he use that isobutene to make the terbutyl ether as a protecting group for alcohols, or did he not cover that either?
No, he definitely used the terbutyl ether.
Okay,
I just don't remember what exactly he did.
right. So the terbutyl ether is put on with isobutene and HF. The trimethylsilyl is usually put on with trimethylsilyl chloride, and often with a base in there like triethylamine, because HCl is the other product. So a mixture of triethylamine and trimethylsilyl chloride will accomplish that. The deprotection conditions for taking this off are to use fluoride ion. Silicon fluorine bonds are very strong. And so we'll do an SN2 reaction and kick out oxygen as the anion. And this is PBAF, which is tetrabutyl ammonium fluoride. And tetrabutyl ammonium fluoride is an anion that makes it organic soluble. Otherwise, it's pretty hard to get the fluoride ion into organic solution, because fluoride ion is a small and very hard anion that's just not soluble in organics. So some source of fluoride, tetrabutyl ammonium fluoride, or TBAF, is the most common way of taking off the silicon protecting group. You can take it off by just treating it with concentrated acid, but the fluoride-based ones are much better. So if you were going to use the TMS group, you would have to oxidize that up and then remove the silicon with the fluoride. So I think, based on what I and Dr. Kushner covered and how much we didn't emphasize that protecting group, problem 17, number 50C, probably would have been a pretty tough problem for you to work on. So that's why I wanted to cover it here. So now you have two different protecting groups that you could use for alcohols if you want to. Questions on this one before we move on to the second quiz question?
I have a question. Will
Yeah.
this also work with the vicinal diols? Because I know we talked about protecting group for 2,6 alcohols.
If you're going to protect the vicinal diols, you usually do that with acetone by making what we call the acetonide. So the TMS group will protect, but it won't differentiate between the two alcohols. You can protect any alcohol, whether it's a vicinal diol or a regular alcohol, with a trimethylsilyl group.
Okay, thank you.
The acetonide is a specific functional group, or specific protecting group for vicinal diols that doesn't work on regular ones. So the second quiz question was actually just a slight modification of problem 34B in chapter 18. Check it, write it out to remember what it was. So I made one small change from problem 18, number 34B. I put a CH3 group here instead of a hydrogen, but other than that, it was identical. And the product we're trying to make has an additional benzyl group. So this is the benzyl group. Which has the abbreviation BN. You often see it as BN. So this is a benzyl group as well. And this might, in some cases, be written BN, COOH-CH3. And when you see that BN, you know it's C6H5CH2. So in this case, we're making a new CC bond here. And now, it is in the alpha position. So this one you're going to make with either enolates or enamines. Or if you look at my videos, the pre-recorded videos, siloenol ethers is another way to do that, which I didn't cover in class. So either we're going to make an enamine first, and because this is at the more substituted side, and enamine makes sense because thermodynamically, the enamine, since that's a enamine formation is an equilibrium reaction, that always yields predominantly the thermodynamic product. So logically, if we treated this with one of those common amines, in the chapter is this one, provolone, it's catalytic, usually 12 molar HCl. And we'll make the enamine, 6-step mechanism to get there. And this will be the major. You might get a little bit of the other. In this case, because the benzene ring is here, having that benzene ring and the double bond adjacent to each other makes it even more stable. So the acidity of these two hydrogens is increased relative to the other ones. Normally a CH2 next to a carbonyl group has a pK of about 20. But in this case, because the benzene ring is there as well, and that allows the negative charge to resonate into the benzene ring, this is going to be even more acidic. Right? Significantly less than 20. Which means you're going to get even more of a dominant major. Instead of that 80-20 mixture, you'll probably get like 95% of this one. So the first step is to protect as enamine. And then that can react spontaneously with alkyl halides. I can't remember if they used the bromide or the chloride. Yeah, they used the bromide in the chapter. So this will then do that SN2 reaction. And because this is also a benzyl position, that SN2 reaction rate is enhanced, again, by overlap between the pi orbital in the benzene ring and the transition state. So we get a really nice reaction to put that benzyl group on here. And we make that aluminium salt, and then acid work on with water. We'll hydrolyze this and convert it back to the carbonyl. So in this case, we're just working with 3 steps. Form the enamine, alkylate, and then hydrolyze the aluminium salt. In chapter 18, problem 34, they asked you for the product, giving you the reagents, so I basically just twisted it and made it into a synthesis problem by giving you the product and asking you for the reagents instead. What would you have done if instead of that product, I had asked you for that one.
go through the enolate ion using LDA.
Yep. So in this case, because the new carbon-carbon bond is over here, at the less substitute position, we want the kinetic product. And the best way to do that would be to treat with LDA and THF to make the enolate ion. And by keeping it cold, we'll generate the kinetic enolate, and then the second step is the same. Is to alkylate that with benzyl bromide, and then aqueous acid workup will get you to the final product. So the kinetic product, LDA, and then alkylation. The thermodynamic product goes through the enamine. And you could have used the silylenol ether, which I won't emphasize here, but if you look at the videos, you'll see the pre-recorded videos, you'll see that. Any questions on the quiz or on that problem 50C that I went over? So I'm going to stop the recording and save this. Let's take our 10-minute break now, and then we will come back and I'll introduce the Wittig and the Horton-Emmons reaction. I'll leave that up. Any questions, feel free to shoot them at me while I'm saving this.